Climate change has already altered life on Earth in alarming ways, but now its impact is reaching beyond our atmosphere, threatening the future of satellite operations in low Earth orbit. A recent study from the Massachusetts Institute of Technology has found that as global temperatures rise due to carbon emissions, the natural cleanup mechanism that removes space debris will weaken. This could result in a dramatic increase in dangerous space junk, shrinking the available orbital space for satellites by up to 82% by the end of the century. This growing problem not only jeopardizes critical satellite infrastructure, but also raises serious concerns about the long-term sustainability of human activities in space. At the heart of this issue is a fundamental but often overlooked consequence of climate change. While greenhouse gases warm the lower atmosphere, they simultaneously cool the upper layers. This cooling reduces air density in the thermosphere, the region where many satellites orbit. Normally, atmospheric drag slowly pulls space debris downward, where it burns up upon re-entry. However, with reduced air density, this natural process weakens, leaving more debris in orbit for longer periods. The result is a space environment that becomes increasingly congested, dangerous, and difficult to manage. The numbers are staggering. Millions of fragments of space debris are currently orbiting Earth, many traveling at speeds exceeding 17,000 miles per hour. Even tiny objects, just a few millimeters wide, can cause catastrophic damage when they collide with operational satellites. Larger fragments, such as broken rocket parts and remnants of past collisions, pose an even greater risk. The 2009 crash between an American Iridium satellite and a defunct Russian satellite created thousands of new pieces of debris, many of which remain in orbit today. With climate change accelerating the accumulation of space junk, the likelihood of similar, or even worse, incidents is increasing. The consequences of this growing problem could be severe. Currently, over 11,900 satellites are in orbit, providing essential services such as GPS navigation, weather forecasting, telecommunications, and environmental monitoring. A more crowded and unpredictable orbital environment increases the risk of collisions, which could lead to a dangerous chain reaction known as the Kessler syndrome. This scenario, in which debris from one collision triggers more collisions, could render some orbital regions unusable, crippling the satellite networks we rely on for daily life. The economic and strategic implications are also troubling. The satellite industry is a multi-billion-dollar sector, critical not only for commercial applications, but also for national security and defense. As space becomes more hazardous, costs will rise for satellite operators, who will need to invest in more shielding, evasive maneuvers, and potential active debris removal technologies. Nations and private companies are already launching satellites at an unprecedented rate, but without improved regulations and solutions for managing orbital debris, the long-term viability of space operations is in question. Despite these warnings, the international response has been slow and fragmented. Many spacefaring nations and private companies have yet to take significant action to curb the problem, and current policies are largely reactive rather than preventative. The reliance on natural atmospheric drag for space debris cleanup has, until now, allowed agencies to avoid investing in costly removal technologies. But as climate change weakens this self-cleaning mechanism, a new approach is urgently needed. Proposed solutions include active debris removal missions, better satellite design to reduce waste, and stricter regulations on satellite launches. Some researchers are exploring technologies such as space harpoons, nets, and laser systems to capture and remove debris. Others suggest that new satellites should be required to include built-in propulsion systems to deorbit themselves after their operational lifespan. However, these solutions require global cooperation and significant funding, two factors that have historically been major obstacles in space governance. The worsening space junk crisis is yet another example of how climate change is reshaping our world in ways we never anticipated. It serves as a stark warning that human actions have far-reaching consequences, extending beyond our planet and into the very infrastructure that supports modern civilization. If left unchecked, the combination of climate change and space debris accumulation could lead to a future where orbital space is no longer safe for satellites, endangering everything from global communications to scientific research. This issue underscores the urgent need for comprehensive climate action. The same carbon emissions that are melting glaciers, intensifying storms, and raising sea levels are also compromising the sustainability of our activities in space. Efforts to reduce greenhouse gas emissions are not just about protecting life on Earth, they are also essential for preserving the technological advancements that define our modern age. The choice is clear: act decisively to mitigate climate change and address space debris, or risk losing access to the orbital highways that drive global progress.